gentlemen.
My fans.
All right. Welcome. Let's see.
Yeah, that's
Got
good.
pleasure for me to introduce Dr. Linda Mertz. Linda got her bachelor's degree here at Wisconsin in or thereabouts, and deliberately,
Poster, it's
I
not
know,
a big secret.
I know, but based on the reaction I heard when she saw it was on the poster, it's been a while. Let's put it that way. And then went on to France. I got a degree in France for,
Yeah, just language.
okay, and then to UCLA where she got her master's and PhD in geography with a focus on climatology. And then from there, made her way eventually to NCAR, where she's been since the 1980s. And currently is the section head for the Regional Integrated Sciences Collective. Has been a senior scientist there since 2002. Throughout her career, Linda's won a number of awards. She's a fellow of the AMS. She shares in the 2007 Nobel Peace Prize, and can take legitimately claim that. Has is AAG, American Association of Geographers,
Yeah.
a Lifetime Achievement Award, and then in 2017 gave the Stephen Schneider Memorial Lecture for AGU, among others. Linda has over 100 peer-reviewed publications, a variety of publications, and focuses on a wide range of research areas, lately on a lot in societal applications. And some of the work that she's done has focused on these large coordinated regional modeling efforts like Cordex and NARCCAP. We'll hear a little bit about that today. Welcome back to Wisconsin, and we're looking forward to your talk.
Thanks, Dan. So, the first big multiple RCM, regional climate model, global climate model program I ran was NARCCAP. How many of you know what NARCCAP is to begin with? All right, it's smattering. Another important question, how many of you are familiar with the basic idea of regional climate model? More. Okay, so I can do something very brief on that. So my talk is indeed on the establishing the scientific value of multiple GCM-RCM simulations. I'm using the example of NARCCAP, and you can see that I have, I didn't do this alone, needless to say, and I have a number of collaborators on this that is turning into a paper any minute now, and I won't read them all off. Anyway, I'm very glad to be back at Wisconsin, since it is my alma mater, and it is both just, it has both changed a lot and not changed a lot. So that's kind of an interesting, edgy situation. I did want to mention that Bucky Badger seems to have really come into his own here. We didn't have all these statues and banners. So that was a bit of a shock. All right, back to the science. So I've neatly prescribed a nice outline for you. I'll describe actually first regional modeling, what the NARCCAP program was about, but also kind of a philosophical scientific issue about how do you determine the scientific value of a program. And I'll explain to you a little bit why I became interested in that theme. And then an overview of how the NARCCAP data have been used, and then I'm going to focus specifically on the examples of key research in the climate analysis parts. And then conclusions, and then I'm going to say a little bit about this follow-on program and a Cordex in which we've also done simulations at higher resolutions. So first of all, just so that everybody's on the same page about the regional modeling strategy, the basic idea is, yes, bad if I tripped over that. So you nest the regional model inside a global model or a reanalyses, and the global model provides the initial conditions, and also the lateral meteorological conditions, basically every 6 or 8 hours, depending on the resolution. And the large-scale response to the forcing, in our case, the greenhouse gases. And then the regional model is providing finer scale tens and even lower, higher resolution rather, response. And so here's a little cartoon that shows this. And these are, I'm showing this even though TAD-CM3 is now an older global climate model, but it's one of them that we used in NARCCAP. And you can see it's pretty coarse. As a matter of fact, when I first looked at this, I thought, oh, look, Florida has escaped from the U.S. and is now floating in the, no, that is supposed to be the Caribbean islands en masse. And then you go down to 50 kilometer and oh looky, you get both Florida and the Caribbean islands, plus, you know, much better resolution of the Rocky Mountains, for example, and you actually see the Great Lakes, plus lakes in Canada. So this just gives you a feel for the difference in resolution. So a quick overview of the program itself. We started it, I think it was finally funded like in 2007 or 8. And finally all of the simulations were finished and made available by, I guess, 2012. There were some challenges about that. Anyway, so the basic idea behind it was to explore multiple uncertainties in regional and global climate models. We used 4 different global models to drive 6 different regional climate models. And we were developing multiple high-resolution, what at that point constituted a high-resolution, regional climate scenarios for use and impacts and adaptation assessments. And the simulations, we did 20 years driven by the NCEP2 reanalysis, then 30-year simulations driven by the current boundary conditions from the GCMs, and then 30 years driven by the future A2 GCMs for mid-21st century. And essentially, if you counted all this 4 by 6, we didn't have enough funding to do the full thing, so we did half of the 4 by 6 matrix. 53 different variables saved at 3-hour intervals, which came up to about 40 terabytes of data, which certainly was not too shabby. Certainly went back when we started. Okay, so here's the matrix, and there's something very special about this matrix. We used a balanced factorial fractional design, which basically means that, in this case, each global model provided boundary conditions for 3 different regional models, and each regional model used 2 different global models. Then we also have in this design, we have some 2 by 2 experiments where we have the same 2 different regional models but driven by the same GCMs. So what's so nice about this matrix? And the amazing thing to me is, to this day, here we are in 2018, I think this is still the only program that actually explicitly designed a statistical framework for the simulations, which is kind of surprising to me, actually, because there are a lot of advantages of having an experimental design. You get more robust estimates of error due to the missing cells if you want to try to fill those in. And it's particularly important for determining the relative contribution of the different factors in an ANOVA setup. And so it provides more robust results. For example, if you wanted to try to figure out, in this result, what was more important, the RCM versus the GCM or some combination? You can best do that when you have this kind of balanced design. Okay, now, determining scientific value. Now, one of the reasons why I decided to work on this was because I found that even some of the agencies that had funded this work, it's funded by DOE, EPA, NSF, and NOAA. All right, so 4 major scientific agencies. But some of the program managers, after the program began, sort of were suggesting, they didn't really think regional modeling was worth much. And I took exception to this, since I devoted a great deal of a number of years of my life to this program. And so I thought, well, let me just show you, like I'll show you that this really was worth something. So that's not the only reason, but that certainly was a factor. So the trick for doing this is that it requires an assessment of all of the literature produced using the data, and there's been a lot of literature. Perhaps you can also compare it with other programs. There have been a lot of these, especially in Europe. You can also say, well, maybe the value is the fact that it's used in other major climate programs, like the National Climate Assessment, which it was. Also, you can dig deeper and say where the articles appear, like how many of them appeared in enunciation journals, and by those I mean things like Science and Nature, Climate Change, and so forth. And you could even, I suppose, do a nice weighting of all the articles with all the impact factors of the journals they appear in. And maybe also if, the program has won awards. So would this be enough? Maybe, maybe not. So, in a more concrete way, one thing, scientific value, did the program reach its goals? That's a pretty basic one. You can also come up with these general quantitative metrics, like the number of journal articles, as I mentioned, the citations of the program, how many articles have referred to it, the number of users that registered to access the data. But really, all of that is nice. Program managers like this stuff. But really, to me, the scientific value is what new climate and impact science and other useful information has been generated through the program. That's a lot harder to do than coming up with nice metrics. So, some of these things. Explore the multiple uncertainties in our GCMs, RCMs. Actually, I cite one of my articles. And yes, I think we really did nail that, and I'll discuss that some more. We certainly developed a lot of multiple high-resolution regional climate scenarios for use in impacts. Yes, and I'll say more about that. We did a lot of evaluation of the regional model performance to establish the differential, what I'll call the differential credibility of the individual simulations for the future, and there's been a lot of articles on that. All right, so some of the nice standard metrics of success. So how many articles and reports have been published that actually use the data, didn't just reference it, but actually use the data set? 175, which to me is pretty darn good. The number of users was over 1,000, and at a certain point we stopped counting and decided to just, let anybody have it without knowing who they were. Citations to the program, about 1,300. We also received the NCAR Outstanding Accomplishment Award in Scientific Technical Achievement in 2015. And once again, these metrics are nice. Obviously, I'm showing them to you to impress you with the importance of this program. But that's not the same thing as really saying what the scientific value was. Now, a little more in the background. So we divided the articles to do this mammoth task of figuring out what did people discover through this data set. We came up with these different categories, and I'm just going to talk about climate analysis articles that include validation, projections, and the explicit exploration of added value of regional climate model. Then a lot of articles there were on extremes, on various timescales, particularly precipitation. The statisticians loved this stuff. They just loved it. I point to Dan because we were talking about statistics earlier today. And they really ran with it and did all these really nice development articles on this. It was very widely used also by the impacts community. As a matter of fact, there are more articles generated from using it for impacts than from the climate analysis. There are some special ones on archiving techniques. This was a big archiving thing. And then the other that I was particularly interested in was the masters and dissertations. that used this, which was probably more than 12, because I just counted ones for 2018. So, before I run on to that, let me say that I would say the peak number at the time, when the peak number of articles was probably about 2014, 13, 14, 15. But I was amazed, going through Google Scholar searches, that still, I found at least 10 different papers that have been published in 2018, which kind of surprised me, just because the data set is getting relatively old, but they're still coming out. Most of those were indeed impacts articles. Oh, also, I did a review of the impacts articles in 2015, which I think, really summarized where they were used and why they used the data. All right, but I'm going to focus on the climate analysis part today, and I'm going to focus on not all topics that were covered in the climate analysis, but some what I considered sort of the major ones that produced what I would call some new science. So one was further experiments in differential weighting, which has to do with not assuming that each model has the same value in terms of the climate it's producing. Another was the exploration of more exotic variables, and this partially has to do with the fact that we saved so much. And so one good colleague of mine, Sarah Pryor, who's a specialist in wind energy, had done some nice papers on looking at high impact, high magnitude winds. I'm going to say a little bit about that. The establishment of added value of RCMs. This is a big topic. There's been just, to use a technical term, oodles of articles written on this topic, and I'm going to show you a couple of those results. But one of, I think, some of the more interesting from a true climate process level is these in-depth process level credibility analyses. A number of done by Bukowski et al., and then Thibault and Seth, for examples. Comparison of downscaling methods. Notice, Vavros and Benke, 2013. And then another important topic, the indications of the limitations of simulations due to the resolution. Like now, 50 kilometers is not exactly considered high. And people are doing a lot of simulations at 4 kilometers. Now, they can't do simulations as long as what we're doing with NA Cortex, and they tend to do it with only one model. One of the strengths of this program is really looking at that uncertainty across the different models. Okay, so our first one is this paper by Sobolowski and Pavelski, 2012, JGR. They looked at the Southeast U.S. climate, and theirs was an example of differential weighting, trying to figure out how should we weight these models to come up with ways of reducing the uncertainty, for example, in projected changes in temperature and precip. So they looked at the current and future runs of 6 of the GCM-RCM pairs. And I will stop there for a second to say, this was something very interesting about developing and running this program, that people started publishing on it before it was finished. And fine, but it also made me think about, so was the pace of this program too slow? The fact that people were jumping out there, and for example, they used only half of the simulations, because those were the only ones that were available when they wrote the article. So that's an interesting problem in terms of managing programs. It's like, can it take too long to finish something? All right, so they used the REA technique developed by Georgi and Mearns, which is a weighting based on 2 criteria, the model biases and the degrees to which the models were converging. So a quick look-see. These are temperature, probability, density functions, both showing the weighted and unweighted for 3 grids. one in East Arkansas, Southeast Louisiana, and North Central North Carolina. And the solid black is showing the PDF. This is also for summer and winter, is the observed, and I think we used the University of Delaware data set, or they used that. The solid blue is just the multi-model mean, with no weighting. So these little lines there. And then the dash equals the REA weighted multi-model mean. Now, several interesting things about this. One is that, sort of to my surprise, the weighting actually worked better in summer than in winter, and I would have expected the reverse of that. But basically, where you see the dashed line and the black line cover one another, that's where the weighting actually best brought the PDF in line with the observations. And that worked quite well in the summer in Arkansas, Louisiana, and somewhat okay for North Central North Carolina. In the winter, at least for these locations, it really didn't work so well. True, in general, the weighted brings it closer to the observations, but not identically. So what these authors concluded was that the weighting scheme results in reduced magnitude and percent area with significant bias for both temperature and precipitation, and that the application of the weighting scheme for future projections reduces uncertainty, e.g. tightens the confidence intervals by as much as 1.6 degrees C, and reduces precipitation uncertainty by as much as 50%. Now, I was marching on. Okay. Personally, I'm not sure I agree with these conclusions, because I'm very concerned about weighting in ways that doesn't truly work. But I'm not going to go into that. I just think the whole issue of weighting is very complicated, and it's not easy to figure out the best way to weight things. But this was indeed their conclusion, so I thought it was a very nice application to weighting, and they did come up with some fairly robust results. Okay, wind analysis, moving on to what I would call exotic variables. So, this is this work by Pryor et al. In 2012, JGR. I'm just going to give you mainly her conclusions. She found that the NARCCAP RCM suite exhibits clear added value compared to the NCEP2 reanalysis. And if you're interested in wind, you should definitely look at this article. Simulations of contemporary wind climates show greater variability, this is a nice piece of information, with RCMs than with the lateral boundary conditions. So that means that the different RCMs are very important for the conclusion. Looking at the future winds, indication of reduction in wind, pretty much in most of the domain, and then didn't see a lot of extreme winds changing substantially, like very high, above the 95th. And I'll show you one graphic from this. So here's the mean and the 95th percentile. And you'll see the red means all decrease, I mean the blue. But interestingly enough, you see this wind increase sort of right in the center area where wind power is really being focused, which is kind of interesting in the US currently. And then you see a decrease in the P95, but a lot of it turns out to be not that significant. So if you're interested in wind, Sarah Pryor is certainly one of the experts in that area, and she's done a lot of great work on it. Added value, very big topic. What is added value? Needless to say, there are many definitions. Added value, I'm just going to say, is basically indicating that the application of the RCM provides some new information that you couldn't get from the GCM that you think is credible. Very general definition. DeLuca et al. 2012-2013 developed a potential added value index, PAV, and he found that as you would expect for added value for RCMs, that you're going to see a lot of it where you have complex topography, because that's what RCMs are going to do particularly well. So he found a lot of potential added value in the coasts and the mountains for precipitation. A different approach was taken by Elguindi and Grunstein, 2013. They used a climate classification as demonstration of added value. And I think this was interesting because it was indeed a robust way to assess a model's ability to reproduce multivariate conditions. And what do I mean by that? Any of you people from a geography department? Two. Oh yeah, Dr. Bird. So here's the revised Thornthwaite climate classification. And this is being developed from the UW observations. So the you have different wetness indications by these general groups of colors, and then within, as the hues change slightly, it's an indication of the degree of temperature, whether it's cold. So for example, Maine, it is going to be wet and cold, so that light blue. And this is, you know, a map that shows the spatial distribution of these different climates. So the idea was, what they did was look at how well did the GCMs and the RCMs do in reproducing it. So I'll show this again. Memorize this. Got it? All right. And here is how a few of the RCM GCM combinations work. Here are two of the GCMs, the CCSM and the HADCM3. And then here are two models that were embedded in the CCSM, and then two that were embedded in the Hadley model. And I would say, just as a quick look-see, that certainly I think that the Hadley HRM3 pretty much got it better than most of the other models that I'm showing you here. Although everybody seemed to have screwed up badly on Florida, except for the global model. So, of course, they have one of these for each of them. Basically, their conclusion is that all of the regional models did better than the GCMs, and hence they considered that to be a measure of added value. I mean, you can argue about a lot of these definitions, but I think this was a creative use of that. Now, differential credibility analysis. I'm going to show you a comparison of 3 studies in 3 different regions, sub-regions of NARCCAP. And this is what I think is some of the most creative work that we have done with this. This was done, our colleagues, Thibault and Seth at the University of Connecticut, and then Melissa Bukowski and colleagues at NCAR. So first of all, what do I mean by differential credibility analysis? I mean that you can really tell on a process level whether you find this simulation more credible in terms of what it can correctly reproduce on a process level than that result over there. And that theoretically, this is what I would say a richer, if you wanted to get into weighting, I'm not sure I am a fan of weighting, I'm kind of agnostic about it at the moment, that this is a deeper and better way to do this, is to really do the hard work of the process level analysis. So, the first one I'm going to show you is the North American monsoon, and I'm going to have to kind of whip through these, but the references are there. So what we did with the monsoon paper, that Melissa in particular, she's a very strong dynamicist and regional modeler. we came up with what we considered to be the major characteristics, mainly on a process level, that you had to kind of get right to be said that you have actually reproduced the processes of the Southwest monsoon. And these include getting the specific humidity right, the position and strength of the monsoon anticyclone, the Gulf of California low-level jet. All right? If you don't get that, one can say, you know, really, have you gotten monsoon at all? And so, rather important, precipitation intensity, other, which, you know, depended upon problems with particular simulations. All right, I'm not going to go into a lot of detail, except to say that we gave every model combination a score of yes or no, did they get it or not? And then we did the very clever math of adding up those values. All right? Now, higher the number, the more things they got right. And interestingly enough, and remember this model combination, the Hadley global model, providing boundary conditions for the Hadley regional model, did best. All right? Got everything right. They got everything right, so they got 7. 7 out of 7. Then there were a couple that did not too bad. One of them was also the HRM3. And the other one was the Hadley global model. So the best models included either the Hadley regional model or the Hadley global model. The poorest, quite frankly, all of those driven by the CCSM were pretty poor, and the MM5 was really poor, and then the RegCM3 driven by the Canadian global model was also poor. So we were pretty happy with this. I mean, it's still a little bonehead, but not horribly bonehead. Here's the Hadley. So here's the difference maybe in terms of what you say about the future. So we established that that Hadley combination is the most credible of the NARCCAP simulations. And that model shows a small but significant decrease in July-August precipitation, right? A decrease of only 3%. If you just took the mean of all the models, the decrease would have been substantially larger, minus 13. And we just simply decided that was really not credible. Now, what's interesting about this is this creates a problem, because one of the things that climate scientists and people who work with users of climate information, you're always supposed to tell the people, never use just one model. Really? I think that's probably not a bad thing to say. But in this case, I mean, you know, you could theoretically say, okay, maybe use the 5 guys. And then actually, we didn't figure out how much of a precipitation change that would have been. But really, we only felt confidence in this final result. Now, and I think we do say that probably on the website for this region, that it really would be a small decrease in precipitation. And we have had some people come back to us and say, but that's only one model. Special case, I don't know, it's not easy saying usually you should use a bunch of models, but in this case, we really think there's only one that is truly credible. Okay. So the problem of what we call useless search.
But you've only determined that by using a number of models.
Yes, of course.
So it seems like you could just answer that back and people should say, oh yeah, well, I'm satisfied. But they're not. It's weird.
Wait.
Okay.
Just you wait.
Okay.
The story gets much more interesting. Actually, I think I'm going to skip this little discussion, except to say I'm just going to show an example of a situation. You know, always saying, well, higher resolution, things get a bit more credible. So Melissa also did a 10-kilometer simulation for this NA monsoon with WRF driven by the CCSM. That model that really does not provide good large-scale boundary conditions. So here is the 50-kilometer one, here is the cycle of precipitation. The observed are here, and neither of the model get a monsoon precipitation signal at all, regardless of the resolution. All right, so now I'm going to go on to the study by Thibault and Seth for the Northeast, towards the credibility of Northeast U.S. summer precip projections in CMIP-5 and NARCCAP simulations. They also looked at the entire CMIP-5 suite. I'm not going to show you that. They came up with, they're also very strong dynamicists, relationships between summer precip and the 500 hectopascal geopotential height, 850 and 500 hectopascal winds, sea level pressure, moisture convergence, pressure presented by the P-E, and also some simpler statistics, let's say mean precip bias and interannual variability. And here are some of the results, the regional results of precip. This is the current period versus OBS. And again, here it's UDEL. And I think I have did little circles, right. So a couple of the regional models got it pretty much right on, MM5 and HADCM3. What's this? CRCM in the CCSM, the model that was horrible in the, no, that's not it, it's the other CCSM, fine, it's still the CCSM. These models did quite well, although I must point out that so did the global Canadian model, did quite well. This is the mean of the observed, and those are, I think, one standard deviation or UO. So from the point of view of just the precipitation, there are problems if you're just going to use precipitation alone as a criterion. There are problems with a lot of them. Now, again, they did a process analysis result, kind of set up similar to us. They have a whole bunch of different criterion. And then they counted how many times did these models get a yes, and figure in the top 4 group. So for example, we've got WRF, GCCSM, what does C stand for? It's one of the better 5. So all the C's here indicate the better models. All right? So they also use criteria appropriate for the Northeast for summer precipitation. And what they came up with, the better 5 NARCCAP models were the WRF-G driven by the Canadian model, Hadley RCM driven by the GFDL, regional climate model, RCM driven by GFDL, MM5 driven by Hadley, and WRF-G driven by CCSM. And then they kind of thought, well, we'll eliminate the lower 4. And looky, one of the ones they eliminated is the model combination that was the best for the Southwest. When I first saw these results, I was doing a talk at a conference on the philosophy of science, and my response to this was, yikes. But it gets worse. Or better, depending upon what you think science should be accomplishing. So here's the map of the percentage change in precip. This is of the better 5 for the summer, and you see, some real serious decreases in the Northeast. So their conclusions were that large-scale processes in RCMs resemble those of the driving GCMs. I didn't really show that. Credible model combinations are identifiable, but they do not provide agreement in direction of change of precipitation. More bad news. these three projected decreases. This combination projected increases, and the WRF CCSM projected mixed increases and decreases. So one of the things that doing this kind of credibility analysis hopefully will do is get beyond these uncomfortable bifurcation of precipitation changes. Not always so. All right, now I'm going to rocket on to the southern Great Plains. This is from Bukowski et al. 2017. Changes in warm season precip in the southern Great Plains. Just cutting to the conclusions here. The increase in mean precip in early spring, intensification of dry season in July and August. And Melissa did a very nice job coming up with the causes of this that seem very credible. Projected northward shift in the mid-latitude upper level jet, expansion of monsoon anticyclone, increase in the strength of the Great Plains low-level jet, and land-atmospheric coupling that initiated earlier in the summer. Now, what's interesting here is that all of the RCM GCM combinations are credible, except for all those driven by the Hadley model. So, I'm not going to go through the causes. So, comparison of the three studies. HAD-RM3, HAD-CM3 is best. All CCSM-driven simulations are poor. To the northeast, that combination is among the four poorer. But other Hadley combinations did fairly well. Southern Great Plains, all of the Hadley-driven simulations are poor. But the regional model HRM3 is okay when driven by other GCMs. So the point is, what does this mean? And what am I going to say about these articles in this grand overview paper? I'm willing to take suggestions. You can just submit them to, yes, do you have a suggestion?
Well, I don't know. What's missing here, and it can be done, is an explicit simulation using the larger scale model, not having a regional model at all, and seeing if it beats the regional models.
You mean at a higher resolution?
At a higher resolution globally.
Not easy to do when the
Well, it's not easy to do, but
models-
maybe you could do just one to see. Because I would suspect the problem is the regional model concept in the first place.
There are many who share your opinion, but not all. I think that'd be difficult to do for NARCCAP because so much has changed, but for some of what we're doing now, that might be possible. And we are doing that essentially in a DOE program. So the reality is that models perform differently depending on the controlling mechanisms. Yes. Can we trust HRM3, HAD-CM3 for the North American monsoon area when it is problematic elsewhere? And so what do you do then, let's say, for the national climate assessment where you want high quality simulations everywhere? I have some ideas, but I probably don't have time for discussing it. Okay, I had to include, of course, the Vavros and Benke study for obvious reasons. It's about Wisconsin, and this was motivated, the study was motivated by concern about public health, diseases that are connected to high precipitation amounts. And they used a downscaling method. I'm not going to go into the details. It's similar to what Wood et al. Used in 2004. It's similar to the bias correction spatial disaggregation method. And they downscaled to 10-kilometer grids across Wisconsin. And they were the first to compare two different downscaling methods to 11 different GCMs. All produced reasonable seasonal and annual precip totals during the historical period. The GCM greatly underestimates extremes, as we expect, based on daily total thresholds in the current period. And both downscaling methods are reasonable. Statistical is a bit better. And I'll just show you, whoops. Oh, I think I forgot to remove a slide. So, great, so I just said everything I was going to say in these two slides. So here's just a graphic from Vavros and Benke percentage changes are similar, even though the absolute values are not. So this is showing the percentage change in the return period for these different thresholds. Okay, so the return period obviously is going to decrease because you're having higher number of extremes. And the best example of that is really at the highest threshold, where really all three of them, this is the NARCCAP, this is the bias correction, spatial disaggregation technique, and here are the GCMs. And you see they're really pretty much all along the line. Now there's a lot else in this article, but on this score, there didn't seem to be a substantial difference from what the statistical and the dynamical were producing. That's, of course, only if you're interested in the percentage change in the return period. Resolution limitations. I'm going to flash through a lot, actually. I'm just going to show you this example. This is some nice work by Wangwala et al. 2012 for the San Juan Mountains in Colorado. And, you know, look, when we were doing this, we knew 50 kilometers was a really great resolution for 2010, let's say. But obviously, many people have gone way beyond that since these simulations were done. So this was projections of temperature extremes in the southern Colorado Rockies. This is the topography when you really zoom in there, and you can see 50 kilometers at this area. It does look coarse. So they found that the different RCMs demonstrate consistency in simulating physical processes that lead to changes in surface energy budgets and warming response on seasonal and elevational scales. Like you see earlier, snowmelt, thawing of soils, moistening of the lower atmosphere in winter, particularly at lower elevations. And one of the main messages is you see large increases in minimum temperature in winter and maximum temperature in summer. And this is a bit washed out, but they created two different elevation zones. Blue is the lower, pink is the higher. Here's the T-min. If you look at winter here, you see that indeed in winter, T-min increases considerably at the higher elevations compared to the lower. Whereas this is just one of the RCN, GCM combinations. For Tmax, in the summer you're going to see a higher elevation, bigger increase in Tmax, and that's what you see here. And they found that these results are consistent with those from observational trends. So this was very nice. I was actually kind of thrilled that even at 50 kilometers, they could tease out this elevational difference. So, further conclusions in comparison to the driving GCMs, the RCMs facilitate an improvement in analysis of processes in mountainous regions due to the increased resolution, but the RCMs are limited by the 50-kilometer resolution, only provide a weak mountain forcing, and you really can't infer effects from 11,000 feet because they don't reach that elevation, and you need to go down to a resolution of about 6 kilometers. All right, one last. Some work that I'm doing with young scientists in my group, Rachel McCrary. And I really like this picture. This is the change in snow from NARCCAP, just for the western U.S. And I'll just point out one thing. You see something very nice that you certainly don't see in any of the global models, that you see increases in snow in January, February, March, along the crest of the Rockies in a number of these, particularly the Canadians. And the Canadian model, quite frankly, the regional model has the best snow physics of all the models, as you might expect in Canada. And you get that in some of the other models, but some of them, like from the Hadley model, you don't get any of that effect at all. So we're teasing out, so why is it that some of these really get that very nice effect and some of them really don't? Grand conclusion. So, where am I with this article? It's still a work in progress, which it should not be. It should have been submitted like a year ago. So I think there are papers, important papers demonstrating the added value. I think the use of more exotic high-frequency variables is important, the wind work. The further exploration of weighting of models. I think there's nice work there. The comparison of downscaling methods, which I desperately think we need to do more of. And then particularly the detailed process level analysis, enriching knowledge of how climate systems work, and the value of downscaling the process level credibility. And then, of course, the resolution advances, but also limitations. So that's where I am with my conclusions with the climate analysis part. It's not bad, but I still don't feel completely satisfied with that answer. But I'm going to leave it there for now. Oh, bad. All right, a few quick words about NA-Cortex. Who knows what NA-Cortex is? All right, great. It's the North American Cortex program. Cortex is an international program of dynamical downscaling, also for North America, blah, 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 doing higher resolutions, 25 and 50 kilometers. It's an RCT 8.5, and we're hosting a whole bunch of the variables at this website, nacortex.org. Here is the chart of the simulations. You notice this design is not terribly balanced. Oh, why is that? Because we can never get funding to actually do the project, and so we had zero control over what people actually used, and just had to, as in beggars can't be choosers. However, it all fell out, but it was kind of nice because the GCM-4 and the WRF became nice sets doing both 25 and 50 kilometers across 3 different GCMs that nicely span the equilibrium climate sensitivity of the CMIP-5 data set. So that was very nice. I'll just quickly show you improvements from NARCCAP. So here we have, these are NA-Cortex. This is just showing Phoenix, showing the precip frequency, GCM in different GCMs, and here's WRF in the different GCMs, and they all pretty much get the frequency curve for the year correct, compared to poor NARCCAP, where things did not look so great. So I think we see a real improvement here. I encourage any of you who are interested in this stuff to go to the NA-Cortex website. Finally, research needs. We really need a more systematic evaluation and comparison of the various downscaling methods to determine which ones do we really trust. This would include high resolution, global climate models, and we're doing that in this program called Facets, funded by DOE. Further investigation of added value, particularly for statistical methods. But we also, it'd be nice if we had a downscaling framework for the U.S. supported by multiple government agencies, so we could actually figure out, for example, what should be being used in the National Climate Assessment. And I think, yay, a little late, but not too bad. Thanks very much. And do these polar bears look sad or what?
They look concerned, for sure.
Concerned.
Thanks. We talked a little bit earlier about what can be done within statistical and dynamical.
Mm-hmm.
And these communities, even within dynamical or statistical, seem to be operating kind of on their own. So it's good to see these coordinated projects
Yes.
bringing people together. I haven't seen that on the statistical side, and I certainly haven't seen that in terms of blending between statistical and dynamical.
You mean like the hybrid methods?
Yeah, or even just what can we, taking advantage of something like this where we can resolve potentially physically consistent processes, but we can't necessarily do large ensembles. Whereas with some sort of combinations where we can test stationarity assumptions or use statistical methods to downscale the dynamical models to test a lot of our theories
Right.
on this. And I'm wondering if you've seen anything like that in that space.
In Europe,
Not a lot, yes.
Doug Mara has done a very nice paper comparing 1 million different statistical downscaling methods in Europe, and I believe they were going to go on to do stuff in combination with Euro Cortex. As I said, we're doing some of that for DOE by combining a bunch of different dynamic downscaling with 4 different statistical methods and a hybrid method. It's not easy to sort out, actually, but I think, and I've talked to some of your colleagues here who are doing some really nice stuff that can feed into that type of comparison. I think it's a shame. I think it's a real waste. And actually, I will tell you all a secret. We tried to get together a workshop on comparing different downscaling methods in the U.S. And the U.S. GCRP, the United States Global Change Research Program, I'm on their advisory board. So they said they were interested in doing this workshop, and then I said, oh, well, maybe not. And we thought, that's odd. Why wouldn't you want to do the workshop? Well, I'm trying to think of a very polite way of saying this. Let's say different agencies become very wedded to particular techniques that they put a lot of money in. And so I think what I was being told in this very sub rosa way was that we don't really want to know the answers. Now, you did not hear this from me. If any program manager comes and yells at me about this, I will find you. I will hunt you down.
I think this is an issue that, I think this is an issue not only in the funding, but also amongst the downscaling communities.
Oh,
There's
absolutely.
a lot of territorialism to this. And I haven't been able to kind of identify why that's the case, except for kind of desire for funding or
Well, I mean, it's tough, you know. I mean, let's take this magnum opus paper I'm trying to write. What if I came to the conclusion, sure, you spent 10 years of your career on this, but, it really wasn't worth very much. It would be hard to do that. So I'm just saying that I can relate to the fact that people get invested in certain things, and it takes a certain very high level of honesty and integrity to just admit, yes, we've dumped millions of dollars down the drain on Acme or whatever. I just, a high resolution GCM. I think it's an interesting problem in how people manage their expectations and how they've spent their time and how honest they feel they can be about, I've wasted the last 10 years of my life. Sure.
We once tried to look at the climatology of the regional model predictions for severe weather over the high plains and see if it matched.
So were these predictions in that they were near-term forecasts?
Daily predictions where, where you
okay.
just have higher resolution over the high plains. They don't match. We can't reproduce the climatology of severe weather from the daily models. That sometimes they look pretty good. They use them judiciously at the SPC to make forecasts for severe weather. If you look at the climatology of what's being predicted, it doesn't look like the severe weather climatology.
Okay.
That's a problem because that's your best case scenario. And in terms of what regional models could possibly do.
Well, that's a long discussion, which I don't think we're going to.
Yeah, but I don't think there's a convergence on the local climatologies for things like the stuff that goes over the high plains. I think there's a little more forgivingness in the southwest monsoon because it's so driven by the topography and the interaction of large scale moisture fields interacting with the topography.
Right.
Whereas the high plains are more convective.
Well, I don't know. I mean,
type
notice,
things.
a lot of those models did not get the monsoon right at all. And it's very interesting to me that NA Cortex, and we haven't sorted out why all the NA Cortex models get it. And that's very interesting. So, but, there probably are regions where nothing works very well.
Yeah.
So I guess people in those regions should just move to a region that we can handle climate.
I once talked to Reed Bryson about this problem before, of all people. But I talked to Reed, and he said, wow, he thinks it's impossible to predict things like severe weather. And he thought the real way around it was you should just use the models to predict shifts in large-scale features and then use statistics of how we are today and just shift it with the shifting patterns. And that would give you a better representation than trying to explicitly run it in models, which can't even do it with the current situation.
Possibly, yeah. I'm going to remain
Yeah, but
strategically agnostic.
I'm not a climatologist. I'm not a climatologist, right? So I'm wondering.
But he knows and interacts with climatologists.
I know some of them. And I know that since the meeting in San Francisco on the Climate Action Summit and the recent report released today from the IPCC, that we have to rapidly decarbonize to stay below 1.5 degrees. So my question comes to your work with Sarah Pryor, actually, looking at changes in wind.
Yes.
I'm wondering if people in energy, as opposed to the impact scientists, people in energy are looking to these future models to see where should they shift their wind farms or solar farms.
Oh, yes, they are. They are all over this.
They are.
I can't attest to everybody they're working with, but they're working with Sarah. They're doing a good job. I can say that. But yeah, they're very interesting. Any questions?
All right, well, thank you. Let's thank Linda once again.
How many of you people went to the football game? Just taking a survey. Oh, and one last thing. So when do you think this picture was taken? It's a picture of a painting. When do you think this painting was painted?
5 years from now.
1890 by a Norwegian.
Close. 1923.
There you go.
By a Norwegian.